on our JChem second webinar. On the first webinar, you may have heard that. I just shortly want to mention what you have heard about. You heard a brief summary about how to connect to database using a connection handler, how to create tables, and we mentioned also the available table types, how to import molecules into tables in a standardized form, and how to create additional columns in this databases, and what are the most important fields, most important common fields of our JChem structure tables. You can find the webinar on our webpage, as János has already mentioned, and we have also code examples that were shown. You can find them on our webpage. Under the examples. I copy the link to you. So all the examples will be shown here. So let's start the today's presentation. We already know almost everything about the database. We can start the database search. Let's start with the queries, one of the most important things that we want to find in a database. What can be a query and what is called a query? A query, sometimes a normal chemical structure, but in most of cases it's not enough for us just to draw a structure. We have to somehow spice it. For example, with charges, as you see here, or we want to use isotopes in the query if we want to match only to specific isotopes, or we are not sure what kind of atom is in a specific position, so we want to enlist the possibilities. In the top left corner you can see an atom list, or the inverse of it, the opposite of it, a negative atom list. That means that you cannot find a carbon, nitrogen, or oxygen. That's in the lower left corner. We have position variation possibilities also, bond variations. For example, you can tell that a bond can be a single or double or single or aromatic bond or any bond. And you can use also some R groups in your query. There are more than about 30 types of query features that you can find in the periodic system under the periodic system icon. They are all mentioned in a query guide. The query guide can be found under your documentation page on ChemAxon web page, the user's guide, JChem Base Query Guide. So we know just roughly what a query is. I will talk about the standardization of the query. We already talked about standardization when we import structures into the database. It's important that we can find them, because in the standardized way we can, for example, find the different forms of aromatic molecules. So we have to standardize also the query in the same way as the molecules are in the database table. So when you start a JChem Base search, the JChem Base takes the query, sends it to the standardizer. The standardizer takes the standardization configuration. It can be given by you as a user, but by default it is loaded from the database table because it is stored in the database table. If you use a standardization configuration on the database table, you won't see anything in the database, but if you have given a custom standardization, then it will be read from the database and applied to the query. Once the standardizer made the standardization, it sends it back to the JChem Base searcher, and the standardized query will be searched against the database. So let's see what the database search is. Now I just want to mention the two main class groups of the search, the searcher classes and the option classes. I will return back here a bit later. Why are these classes so important? Because you have to know exactly what type of search you want to perform. The most important search option is what type of search are you interested in. We have 6 kinds of searches. The first is substructure search. If you perform a substructure search, the query should be a subgraph of the target, what can be found in the database. And here you can see some examples what are retrieved and what molecules are not retrieved from the database. As you can see in the retrieved column, in the first example, the structure can be exactly the same, just like the query, but that doesn't matter. The important is that it has to be a substructure of the query. Superstructure search is the opposite of this. The query should be a superstructure of the target that is in the database. I have to mention that usually superstructure search is used only in case of query tables. So when you store your queries in the database table and you have large complex molecules that you want to search, you can use the superstructure search against your query table. For query tables, superstructure search is the default search mode. For all other tables, substructure is the default search. Full structure requires that the whole graph, as it is composed by the heavy atoms, should be the same, just like in the target. You can see that in the retrieved column in this second example, you can see a stereo center. There's a rule for that if there is no specific stereo center or charge in the query, then it will match every specific stereo or charge in the target. I will see examples for that later. For full fragment search, it's just like full structure, but not the whole structure, whole target structure should be matched, but only one fragment of it, as it's seen in the first example in the retrieved column. Duplicate search is the most strict search type. You have to exactly match the query. And finally, similarity search is, like it says itself, just search for similarities, and it's based on our fingerprint that will be also discussed later. So it cannot predicted what kind of molecules will be found in the database, but we hope that are very similar to our query. You can give also a threshold that will give a limit to our similarity. The higher the dissimilarity limit is, the more structures we will find. So let's start on some other search options that are interesting for you. I already mentioned that you can search for charges, isotopes, and also you can search for radicals and valence. You can use this in the queries. The main rule, what I've already mentioned, that you can set these options to on, exact, or ignore. By default, the value is on. It means that if there is no specific feature, for example, no charge in the query, then it will match both versions of the target, also the charged and the non-charged version. But if you use a charge in the query, then it won't match a non-charged target, only the charged one. It's also true for isotopes, radicals, and valences. When you set this option on exact, then different types won't match. So non-charged won't match the charged, charged won't match the non-charged. And if you ignore it, then every mixture of queries and targets will match. Another type of search options, if you set how stereo centers match each other. It has many different values. Let's see them. The default value is on. On the left side, you see three structures. In the bottom, it has no indicated stereo center. On the top, the two molecules are the mirror images of each other, and they have both stereo centers indicated. So let's see if the bottom is the query. The green arrows shows that it will match both the left and right side stereo center. Just like we shown in the case of charges, if there is no indicated stereo center, it will match the indicated one. On the right side, you can see the double bond stereo conformations. In the bottom, you can see a wiggly bond that indicates that it has a stereo center, but we don't know which one. That's cis or trans stereo conformation, but it will match both the cis and trans conformations if the search options is set on its default value. The next value is exact. Then none of the group on the left and on the right will match each other because we expect exact match. If we set it to enantiomer or diastereomer, then the non-indicated stereo center, let's concentrate on the left side, will match both indicated stereo centers, and the left and right stereo center will match each other because they are the enantiomers of each other. It's similar to the double bond stereo matching the cis and trans will match each other in this case. And finally, if we set it off, then you can see that all pairs of clears and targets in each direction will match each other, because there is no distinction between any stereo indications. The next search options what I would like to talk about is the tautomer search. You may know that some molecules have different conformations that can change into each other easily. They are called tautomers, and it's usually a single bond, double bond change in the conformation, and some of these changes can cause multiple tautomers for one structures. The tautomer search options has an off and on position where you default is off, but if you set it on, then the tautomers of the same molecule will be found as matching molecules. Well, that's an interesting one, the wake bond search levels. As it says, you can somehow find what you don't find in another way. For example, you can see a 5-member ring on the left side. That's not an aromatic ring, so if you try to match it on the right side molecule that contains only aromatized rings, it won't match. But if you use our default wake bond search level, it says that 5-member ring will be taken as if their bonds were single or aromatic or double or aromatic bonds. And in this case, the left side structure will match the right side because the or aromatic bond will match the aromatic bonds on the right side. So on our default level, all the 5-membered rings will get an or aromatic tag on their bonds, and also bridging single bonds between aromatic rings and also single bonds on an aromatic ring. You can find description about wake bond matching here. I send you the link. It's also on our web page. Sorry, I will send it later. You can find it starting in the query guide as well. But if it's not enough for you that the 5-member rings will match aromatic rings, then you can go further. You can say that every bond can be or aromatic. So in this case, the left side structure will match the aromatic bonds, or you can totally ignore type. That's the highest wake bond search level. In this case, every 5-membered ring will match every other 5-member ring. You may also attach data to your structures. It means that you specify a group and add a label to it. For example, if it's unstable, and you can add the property and the value, its stability is unstable. And in your search, you can use these data labels if you are interested only in those molecules that are unstable or stable. For finding the structures, you should also set this attach data search option on. Well, I now go back. Now I saw the search options, some search options, they are not all of them. And let's see a bit these classes, the searchers and the option classes. Mainly, there are two parts of our searches, the memory search and the database search. On the left side, you can see the memory search classes, more search and standardized more search. I will mention them next week. And this week, we are proceeding further to JChemSearch, that is our database search class. Both search class types takes an option class. For more search and standardized more search, we use the more search options. For JChemSearch, we use the JChemSearch options. They have a common ancestor, the search options. It's not instantiated during programming, only the more search options or JChemSearch options classes. And now let's see how to use these JChemSearch options. When you decided what kind of search options you want to use, first you have to instantiate the appropriate search options class. In our case, it's a JChemSearch options class, and in its constructor, you have to define the search type of the 6 types. In this case, we used similarity search. Then you can set in this object the search options. You can use directly addressed search option setters, for example, the vague one level, and the appropriate constants are contained in the search constants class. The default level for vague one level is level 1. Another method to set options directly using a string, where you can concatenate all the search options in one term. JChemSearch options also have some modifiers that can modify your results. For example, you can set the maximum result count. Then it will run only until it finds, in this case, 10 matches. You can set the maximum times in milliseconds. And you can also set whether you are interested in the hits or the non-hits. Default is, as you hope, is the hits, but you can switch it off, and in that case you will get back the non-hits. So how to run a search? We have already created the JChemSearch options object. Now we instantiate the JChemSearch class for database search. This will be seen in search-util Java. Then you can set the connection handler. As I mentioned, it's already taken somehow. Set the query structure and set the structure table on which you want to perform the search. And finally, you will use the prepared set search options. And there's nothing left than to run the search and then somehow retrieve the results. In the cartridge, it can be solved in one row. You can use the JC compare function, and it has some arguments. Smiles, it shows the column on which you want to perform the search in the table. Then you can enlist all your queries separated by a space, and then your search options. The function gives 1 back if it matches the query, and gives back 0 if the target does not match the query. So let's see some examples now.
Welcome to GoToWebinar web events.
I want to show you the search util class. It mainly contains only that rows that I showed you. It will be used in the create JChemSearch method, and it will be called from other code examples. The other what I wanted to show you is the search types example. Let's see that example in a bit more detailed. When I run it, it starts in the main method and instantiates the search types example, and run method is called. It connects to the database and gives back the connection handler, sets up a default table, and runs searches on it. Different types of searches will be run. First, a substructure, then a no atom by atom search, a similarity search, and superstructure search. As you see, we instantiate the JChemSearchOptions first, then we call the mentioned create JChemSearch method with the appropriate parameters, the connection handler, the query, the table name on which we want to search, and the predefined JChemSearchOptions. Then we run it and print the result message of the JChemSearch class. If you see the other cases, they have the same structure. I would like to talk a bit about this print result message, because you may be interested how to retrieve your results. There are some basic results here only, but you can show only also the ID list as well. Now we show only the result count and the search time of the search. Let's run it and see what happens. We connect it to the database table, set up the molecule table, and search on it. The first is the substructure search. The second is a no atom by atom search. I will make a short curve about it later in 1 second, but I show you the result of the superstructure search. Sorry, the third is a similarity search, and the last is the superstructure search. So in the first row we found 21 hits by substructure search and 21 hits by no atom by atom search. What does it mean? I haven't mentioned it. It's not of the 6 search types. Well, it's a special search. And to understand really what it is, we have to go back a bit. Let's talk about fingerprints. In the first presentation, Robert has showed you the columns in the database table and mention that we have fingerprints. Now I will show you what are fingerprints. If you have a lot of structures in a table, and we have really huge database tables, sometimes 10 million structures in a table, the search can be very slow if we want to perform a subgraph search on each molecule. So somehow we want to filter them. If we can find an effective method for filtering, then the screened molecules, during the screening, we reduce the number of those structures. The screen structures should be searched by an atom-by-atom search only, and it reduces the time that the search needs. How the screening is done? Using the fingerprints. Fingerprints is created from one structure. For example, you can see a structure that contains 6 atoms and 6 bonds. We take small paths of this molecule. First, we take only the atoms. On the top left corner you can see the oxygen, nitrogen, carbon atoms. Then we take the single bonds. Single bond that connects oxygen to carbon, a double bond that connects the carbon to the oxygen, and so on. Then we take the longer paths as well. And then we map these structures, substructures, to a bit in a long bit stream. If a substructure is present, then we set its bit in the bit stream to 1, otherwise it remains 0. It is possible that, as it's seen in the bottom right corner, some bits are collide, but that doesn't matter. What are these fingerprints is good for? If we take the fingerprint of the target and the query, then if we take all the substructures of the query, it has to be found in the target as well. So if we take the query fingerprint and match it against the target fingerprints, and we find even one bit that is 0 in the target, that is 1 in the query, then we can drop out the target structure that cannot be hit because it doesn't contain a substructure that is present in the query. You will see that this screening is very effective when we go back to the example, but I would like to show you now how we use this fingerprint and how we use the cache to store them. The fingerprint and the standardized structure that is used during the search is stored in the database. It would be very slow if we could use only database access to search these structures. So at the beginning of the database search, we load them into memory, into the JChem cache. From here, the JChemSearch retrieves the standardized structures and fingerprints, makes the screening, and does the atom-by-atom search. So that's the magic word, atom-by-atom search. Plus, and sorry, can you hear me? Okay, lots of noise, not good. Better? Is it still better? Okay, then I follow. So, the JChemSearch uses the cache for searches, but in some cases cannot find the information in the cache, then it goes back to the database, retrieves the original structure that is also stored in the database, then it has to standardize it and use for the search. It's much slower than using the cache, so we prefer the cache, but there are some cases where we cannot use the cache. For example, if the structure stored in the database cannot be exported to ChemAxon Smarts format or ChemAxon Smiles format, then the standardized structure field is left empty in the database, and we have to use the original structure during the search. As I mentioned, storing the structures in the cache has a big effect on search speed, since we can use directly from there the standardized molecule and the fingerprint. Now I go back to the example and show you the first two results. 21 hits found by the substructure search and 21 hits found by the no atom by atom search. The substructure search takes the values from the cache, makes the screening, and does the atom by atom search on the screened structures. The no atom by atom search does only the screening and go on the atom by atom search part, but it also finds 21 hits. I have to mention that it can be not a correct value, because the screening can left some superfluous possible hits that can be filtered out by the atom search, but in this case the screening was very, very effective. It finds the same hits as the more detailed substructure search. So screening is really a very effective tool in our hands. So let's go back to the presentation. And now we know how to create a JChemSearch object, how to set the options, and how to run a JChemSearch. If you want, you can reuse your objects. You can set other search options in your search options class and run the query with that. But be careful. If you set a search options again, then you call the set search options method on your JChemSearch object and just run after that. In this example, you can see that you set an option, wake bond levels is set to 3, and you have to set it again. Or another method, to get the search options class from the JChemSearch class directly and call the set option method on this returned JChemSearch options. In this case, you don't have to use the set search options again. Now we know the basics of the database search. Let's see some other examples. For example, if you start a database search, you have to wait until it finishes. But you don't necessarily do that. You can run the search in a separate thread. You simply set run mode on the JChemSearch object to asynchronous mode and then run the JChemSearch. Your program will return and you can do other programming as well during that time. And during the JChemSearch runs, you can ask its state. While it is running, you can get its progress message, you can get where it is, how many results, how many hits has it already found, and you can get the current ID. It shows the ID where in the database, so the state of the database search at which ID has already reached and checked against the query. Finally, if it finishes the running, you can print out the result count. Let's see an example about similarity search, also because it's a bit there are different similarity type searches. You can use our built-in similarity search that is based on fingerprint similarity. You can give the search type to the JChemSearchOptions and set the dissimilarity threshold. It means that the similarity should be at least 60% the target. Be careful, it is dissimilarity threshold, not similarity threshold. But you can also use other descriptors. For using other descriptors, you have to create a descriptor table. You have to take a molecule descriptor generator class, set in the descriptor. It's called myDescriptor. It will use the ECFP method. You can also add some settings to the ECFP method, and you can also add a comment to it. Then init the generator and run it. It will create the descriptor table. What kind of descriptors you can use? Sorry, you have to set naturally this descriptor to the JChemSearchOptions. So you have to give the descriptor name to the search. What kind of descriptors we have? We have ECFP, FCFP. They use extended connectivity, fingerprint, pharmacophore fingerprint, B-cut, and the default chemical fingerprint. And also you can use various metrics to compare two descriptors. You can use the Tanimoto, Euclidean, and so on metrics. I show you this search similarity example. What will we do here? We will also set up a table, generate the descriptors, as I mentioned. Here you can set the connection handler and the structure table name to which the descriptor table will be attached, and create 4 descriptors: PF, H donor, H acceptor. Then you init and run for creating the descriptor tables. After that, we perform a simple similarity search. It means that we will use the default fingerprint, then similarity search using the descriptor tables. Performing the normal similarity search is simple. You have to set the JChemSearchOptions type to similarity search, create the JChemSearch object, set a dissimilarity threshold, give the search options to the JChemSearch class, and also the query, and run it. Here we will print the CD IDs that are returned. That's a new method. By calling the getResults method, you will get all the CD IDs in the database table that will match the query, and you can also print it out. In the other method, when we use the similarity search and descriptor tables, we also have a similarity search, create a threshold and a searcher class, and for each descriptors we will set in the JChemSearchOptions the descriptor name, give the descriptor to the searcher class, also the query, and run it. That's so simple. Let's see what happens if you run it. So we are generating the descriptors now. There will be descriptor tables in the database as well. I will show them later. Well, it seems to be a bit slow now. Well, while it runs, I show you the next thing. I think that will be the last one that I will show you. We can also apply pre-filtering on the tables and orderings. What it means, you can give a SQL query on the table that filters the possible hits. For example, we are interested only in structures that has mole weight less than 500. Then you have to write a SQL select statement that returns only one field, the CD ID from the table. But the other parts of the SQL statement can be optional. The most important thing that you have to return one field with an integer value that contains the possible hits. It can be also used for ordering, so you can order by mole weight in this example. And you can also use a joint table or not a joint table in the database, where we have a stock table that contains the quantity of the remained structures in our stock. Then you can select those CD IDs from the stock table, not from the JChem table, but the stock table, where the quantity is bigger than 20, and your search will run only on these structures. So let's see whether it's finished. Yes, it's already finished. If you see well, then when we use the chemical hashed fingerprint, it gives back 8 similar structures. When we use the pharmacophore descriptor, it returns 130. And by using the H donor and H acceptor descriptors, they return the same amount of queries. So you can use different descriptors to get your similar structures. Well, that's the end of our today's presentation. We will follow it next Wednesday.